Quick announcements before we get started. I owe you a study guide today that will be arriving on Canvas before the end of the day, but I have not made it yet, so it's probably going to be sometime this afternoon. That means there's an exam a week from today. Well, that also means that there's going to be a study session at some point next week. Planned for on Monday. I will ask you what day of next week you'd like that to be. And I usually do it the day before the exam, but I could do it Wednesday if the result of that would be a little bit easier to have a little bit more time between that and the exam. So we'll vote on that on Monday.
We do multiple days.
We could, we could say, let's do it Wednesday. And if we feel like there's something left over on Wednesday to further address, we could decide on Wednesday that another day of study would be good.
Hearing we can't just study from Monday till Friday.
There's a good bit here. We've already covered quite a bit, and I think that means that we should take the time that it requires to make sure we feel as prepared as we can before the exam. Last time we were just starting deletion on ABL trees. We had discussed deleting G. We've been trying to modify this image to do that because deleting G meant that there was an imbalance around F and then an imbalance around H at the end of that. So we had a two-step deletion to go through. Sorry?
I thought we got through that, didn't we?
We did get through it, but I think I did not fully draw the final solution on them. So maybe just a show of hands, who has a solution to deleting G on paper?
I'm not entirely sure I do.
So we should probably finish that off before we go on to the next deletion. So I'm going to go through it and make sure we actually have it. So if we're deleting G, that node is gone. So we're going to be walking upwards through the path to the root to see if there are any imbalances and making the associated changes. So when we reduce the height of the right subtree of F by 1, this left slant becomes a double left slant, which says we need to rotate around it. Luckily for the F, it's very straightforward. This is a left of left that is the problem. So this says we just need a right rotation around F. And I think I'm going to try to redraw the entire tree on the other side, just because it will make life a little bit easier as we go through the next part of this. So we have H. I'm going to put the node name inside of the node so they're not on the side like they are at the moment. We have H to C to A, B. From C, now we're going to have E on its right child as left child D, right child F. That's our left-hand side of the tree after that rebalance. Right-hand side of the tree stays exactly the same. We're going to have U on this level, A and W. From K, we have J and P. W, we have B and Y. Y, we have X. P, we're fine. From P, we have M and R. J, we just have I. M, we have L. N, from R, we have Q and S. All right, I hope that was worth the time. Is the imbalance apparent here? I try to draw things reasonably on the same level, that we're on the same level. That is surprisingly challenging for my second grade artistic skills. But from the root's perspective, the left subtree is at depth too shallower than the right subtree. So that tells us we need to do a rotation. If we're looking at where the problem is, from here, it's going to be a right and then left. So we first need to do that right rotation around U before we do a left rotation around H. So to do that, we're going to bring everything from the left subtree up. And as we do that, the P and the associated subtree are going to get orphaned. So let's do this. We're going to bring down the U. Going to bring, we're going to have to bring over the P here. So this V gets reinserted here.
No, W gets put there, then
Yeah.
V is orphaned, then it's connected to W, I don't need to continue.
W. Then was this X or Y?
X,
This should
Actually,
be
no.
Y before
yeah,
X.
no, Y before, it's my fault. Should've seen
All right.
that.
This is going to be the P subtree. And again, instead of drawing it, I think it makes a lot of sense to just reattach. It's a little ugly at this point to kind of visualize the P being to the left of the U still where I originally drawn it. But reinserting there looks a lot better. Means that it shows that you don't have to change any of these associated connections to do that. But now the deep problem is on the right side. So it's created a right of right problem. So now we bring up K. Now we bring up J. Now we bring up I. And this node goes away. So now we haven't solved the issue, but we've moved it from the left subtree of the right child of H to the right subtree of the right child of H. And that's important for the left rotation around H for that reason. So as we move K up, we're going to be orphaning the J. That's going to get reinserted on the other side as we do that. So let's move everything down and create room for things. So we move down the H, down the C,
Wait, oh,
then E becomes C's. This stays the same. You don't have to move this at all. The pointers stay in the same place. F. How do we do this? It was E and F and G. How does it
B
work?
is the left child and E.
E is no. This is
D is the left child, F is the right.
of E. Okay, there we go. That's been moved down, so we can move up the K. We can reattach the J there. Then we move up the U. Then everything else stays the same. So U's left child is still P, and U's right child is W. That's a little ugly,
It is, but it
but
works.
we have an answer. And so we have a left subtree depth of the root now of 1, 2, 3, 4. On the right side, 1, 2, 3, 4. They look like they're at the wrong levels, but these are actually now the same level of depth on the left and right subtree.
Yeah, I thought so too.
Okay. Phew.
That is a lot, yo.
Does it look balanced? Are there any nodes that are imbalanced?
I don't see any, truly.
Yeah, that looks good to me. So the next step would be from here to delete I. Does that create an issue anywhere?
Let's. Yeah, probably. Let's find out, why don't we?
Yeah. Great picture.
It definitely does.
We not start off with like simple delete.
We could have.
What's the fun of that, eh? Yeah, let's,
Yeah, let's draw out the tree, the changes that we make will come together and actually do it.
okay, let's see. Uh, It does create. It does create a little balance. Let's see. Oh, yeah, definitely. See on the left side, but. Not so much on the right so far. Oh, wait. Oh, yeah. It's going to be.
Creates a little bit of an interesting situation.
Yeah, it does.
Because where's the issue? Is it left, left, or left, right?
Can you just choose at that point?
Yeah,
Probably,
either one will work. So you could either do a right rotation and then a left rotation, or just a left rotation. Which one of those is easier?
probably left, right.
Just left is gonna be significantly easier, instead of trying to right rotate around C, which is gonna orphan just the D, and then left rotate around the H, which is gonna orphan this entire sub branch. As we make this longer and then rotate that up and that down. If we just left rotate, we're orphaning a much larger subtree, this EDF. But attaching that subtree is still the same amount of work as it is to attach a single node, because the entirety of the structure stays together. The D and the F stay the children of E. So when you reattach E on the other side of the tree, there's no further connection required. So it is just strictly left work. So let's do that. Let's just right rotate around H.
I was really confused as you're saying left rotate.
Sorry, was I saying left?
Yes.
I think I don't have dyslexia, but teaching makes you re-evaluate everything you think you know about yourself. Great. Yeah, sorry, instead of a left around C, right around H, you can just have the right around H, and that orphans just the EDF. Feel free to call me out if I say something that makes no sense. It probably makes no sense. All right, so to do this, we're gonna bring up everything from the left subtree. So H is going to go rotated down here. In this case, J stays the child of that, but J is now going to be its right child. I'm going to redraw this because it's too far on the other side. This is going to be H, then J. We bring up C. We bring up A. Now, the right child of A is going to be B, but this becomes the left child of H now. And this now has, I have left myself absolutely no room, so I'm gonna need to redraw that. Okay, that should be it. Are we balanced together? If we go back to K, is there an issue?
Uh. That's 1, 2, 3, 4.
We are good.
1, 2, 3. Yeah, we seem to be balanced at least. Now let's go to.
Okay. What happens if we delete J?
Let's see, that's. Ah. Yet another case with depth issue on the left side. And one that is still actually fairly simple.
Almost like you're deleting the ones that are gonna give me a problem or something.
So it's kind of to test us, I think. How far?
That's kind of the problem with ABL over red black is that every single insertion or deletion is relatively likely to cause some problem at some point. So you're actually quite likely to be going through a rotation, at least one rotation on every insertion and deletion. Red black solves that a little bit, but the trees look way worse in that they can be half or twice as deep between the left subtree and the right subtree. No trade-offs.
Okay. Yeah. No.
How are we doing? Looks like either most people are staring at the board or it look like they're done. Which one is it?
Let's finish writing it down.
Getting rid of J.
Interesting. All right. Yep, that's exactly what I did too. Oh yeah, you read my mind.
That should be everything from that small change, that local change at the H node level. As we go back up from there, issue at C. No, 2 on this side, 3 on that side, that's okay. For K, maximum depth on the left side, 1, 2, 3, 4, right side, 1, 2, 3, 4. Back to good again. That one
Yeah.
was easier than a couple of the last ones. So last one here, let's delete B.
Oh yay.
Which
B.
one? B.
Excellent. That creates imbalance there. Blah blah blah. Another drill. Oh wait. Oh. Okay. How could it be so blind? fine. Yeah. Let's see.
Locally, shallowest issue is at W. We need a right rotate around Y and a left rotate around W in order to fix that. So I'm just gonna think in my head rather than draw out the first step, second step at this point, that the X and the Y are gonna flip X here, Y there, then rotate around that. That's gonna bring X from here up. And X's left child is going to be W and right child is going to be Y.
Yep, that's about right.
Looking back at parents, is there an issue between, or is there an issue at U?
No.
No.
Is there an issue at K?
2, 4, 1, 2, 1. Yeah, no.
There's not. So we are done at this point. I want to make one more example that's not directly on the slide for how we would do something like a two-child delete in this case.
Oh boy.
So if we wanted to do something like delete U at this point, what is the easiest way, or what is one way to think of deleting U? How would we go about that process?
Either find like the next lowest or the next highest, and just replace them, or like switch them.
Yeah. So which one do we want to do? Next lowest or next highest?
Lowest.
The easiest one to make sure that we're doing the least balancing possible will be to look at the slant of this node and replace with the next highest or next lowest down the deeper of those subtrees. Since the left subtree is deeper, it's less likely we're going to have to go through a rebalance if we pull a node from the bottom level here as opposed to the bottom level here. Does that make intuitive sense?
Yeah, it does enough.
So when you have a choice as to whether to go down the left or the right, you either bias it the same way each time, which may lead to more rotations, or one that makes it less likely you're going to go through a rotation. So if we pull from something that is less than U, we're going to go to P, down its left child, everything in this subtree is less than U, but the item that is closest to U is going to be the right child of the right child of the right child all the way down to this node. As soon as that doesn't have a right child anymore, we're going to swap the value of S with the value for U. And we're going to recursively, instead of trying to delete this node, we're going to go down and delete this node.
Okay.
So now U goes away. And looking back at parents, is there an issue at R? No. Is there an issue with P? No. At S? No.
no.
At K? No. So you're less likely to do rotations if you check for and go down the path of the slant rather than just always going down the left subtree or the right subtree.
Okay.
I don't have that expectation that you implement it that way, but it might make your life ever so slightly easier to consider it. Questions on this? Yeah.
I think you mentioned that we can stop at one point going up the tree. Like if we go up and there's no change, then we don't need to go past that.
If there hasn't been a change, I don't think there's any guarantee that it hasn't made an issue at some level. But you can, let's see, when can you stop early?
Really only if you're inserting, if you go.
Yeah.
To.
Yeah, it's on insert. On delete, you don't really get a guarantee. So I have a bit more example prepared here. Want to query the class at the moment, show a thumbs. How do we feel about deleting and rebalancing off of those deletions?
Better.
So I see reasonably good here, somewhere between kind of up at a slant and up. So I can go over these examples, but I can also leave them for you to practice on if that would make more sense. So based on the tree that we constructed at the end of the insertion, we can now go back and start to delete from that. And then I have a couple more from the original tree. Show of hands, who would like to go over this? And who would like to leave this to your own practice? Come to me if you have questions with it, or go over it in office hours if people have questions. Looks like that is winning. If you have an opinion on remotely, you can type it in chat as well, and I will consider it. Or message it to me individually if you don't want others to know how you're voting.
You have the tree that you could show us, I don't know if I'm.
I did not write it down. I was gonna rely on at least one student having it in its old form, otherwise I would be useless.
Then from the original tree that we did.
I have the original tree. Yeah, for I guess if the question is from the original tree. So I'll get rid of all of this.
I don't remember that.
Yeah, I can at least get people the original tree. So that you can use this for practice.
And just have us build up the other one, so we can finally delete 13.
Yeah, if you're voting and would like some extra practice with this, come see me during office hours and I'd be happy to go through this then. So there was the original tree,
Let's see, I think we're going on.
or this was this one.
Yeah, that's the one.
Yeah.
So we
That's the
created the.
Yep,
Yes, we did.
and I don't have the tree that we drew from that. So as long as somebody does, they can post it somewhere. Otherwise, it's not too bad to go through the work of practicing this again anyway. Okay, let's talk about implementation a little bit, because this is reasonably important. This is the last thing we'll cover with regards to AVL before we move on to another very exciting topic. So we assume that we start with a pre-built binary search tree, and if we've seen the assignment that got posted reasonably late last night, the expectation is that we are starting with a binary search tree. Again, if you have any questions about putting that together, if you don't have one on hand and you run into any issues there whatsoever, I'm happy to help you get to the point of having this pre-built binary search tree. So we just need to add rotate methods for each case, except that we don't really need a separate method for every case. We will end up implementing them, but some of them are going to be easier than others. And the reason is that my recommendation is you make only two methods for this, a that has any logical juice, that is the left rotate and the right rotate, and it should take a node upon which to left rotate or right rotate. Then if you have a case that is a left-right rotation, you're going to call the right rotate on the appropriate node and then the left rotate on the appropriate node. And there is no further logic required about the right-left rotation than just calling the rotations that you've already written for just the left and just the right. You just change which node you're calling it on, and you can reuse all of that logic. You don't need to redo all of that work, leave yourself open to bugs from what is going to be the equivalent of code duplication. Yeah.
I would be thinking about this too much, but would we make a method for each case, but only two of them would actually have the logic of the actual
Right.
rotation?
Yeah, you'd have a left-right that's going to say if you have a node that is current, then you're going to, if this is a left-right rotation, then you're going to left rotate around the right child, left child, and then right rotate around the parent.
Okay, so you're just gonna have a lot of bigger methods.
Yeah. Yeah, code reuse wherever you can makes your life a lot easier, and this is one of those places where we can really make use of that extra code reuse. Reinventing the wheel is for the Stone Age. Leave it in the Stone Age. So the only changes that we need to make are inside of insert and delete. And at that point, we will just call the same balance procedure at the end of an insert or delete, and you're going to call it on a node that is again going to walk up parent to parent to parent to parent through the ancestor tree to the root and check and change balance factors. So you will need to modify those balance factors for every node that you consider. I'm going to leave that to you to figure out the algorithm for how do those change. If you don't know where to start drawing out some examples of insertions and deletions and see if you can come up with the general set of steps. What checks do we need to make? What are the edge cases? What makes this difficult is if you don't visualize or think of all of the edge cases. So what happens if you're orphaning a node? If you don't have orphan reattachment logic, or it's not always right, then there will be some case for which you find that your tree is not in the appropriate form after you perform that. If you've built this tree with the associated traversals that are required, you can visualize the end tree relatively easily. What I will recommend is if you are using, I think if you're using IntelliJ, then you can use the JGrasp plugin, which allows you to easily visualize things like trees. You can actually look at the tree rather than relying on your in-order traversal printing method in order to see the associated nodes and orders and connections. So feel free to use a plugin that's just this. I think it was the JGrasp plugin.
Okay.
No, I was typing into chat just so that everyone else has the name there as well.
Just J and grasp.
Yeah, if you took 210 here, that was the IDE that you used. And I think that plugin, if I recall correctly, is the one that allows you to visualize the trees without any additional logic on your part. It can be a little bit interesting if you're printing things out on level order to actually go through the work of what is a child of what, where, actually visualizing the logic of the tree. And you're at least as likely to make a mistake from just reading your output wrong as you are from actually making the code error. Yeah, the conclusion at this point is no further logic is needed to make sure that the tree is balanced if we go through that process. Questions or concerns on getting started with this assignment? The associated steps that are required? Okay. On we go. This is a big transition in the class. We're going from, we started with an analysis of algorithms topic, and then we went into more of a data structures topic with binary search trees, and then augmenting them with an algorithm to relay and allow it to be more efficient. We're going to, for the next at least couple of chapters, be talking about a general algorithmic procedure that allows us to take what is brute force, a very expensive process, and create a solution to that that is significantly more efficient. So this is applicable in so many different ways and places and areas, and an understanding of dynamic programming is, in my view, it's not one of the fundamental concepts, but it is one of the most important in terms of those who write code in order for it to compile and work and pass the tests, and those who are capable of understanding when a problem breaks down into something that can be improved. asymptotically. So the motivation for dynamic programming, I remember the mood I was in when I wrote this slide. It was a very interesting mood, and you will see so momentarily. So show of hands, who likes doing the same repetitive task over and over again? Interesting computer scientists.
Not
All right. The follow-up question I have for you is, who likes doing the same repetitive task over and over again? Raise your hand. All right, the follow-up question to that, who likes doing the same repetitive task over and over again? The follow-up question to that. So recognizing when we're doing the same repetitive task, there are ways that you can do this in terms of just code, recognizing that I have methods that do the same work. An example of that we just saw with AVL. If you're going to try to make a left-right rotation, you could either reinvent all of that logic from scratch, or you could recognize that there's some reuse. Instead of writing more code, I should just call the code that's already been written. In the same way, some problems break down in such a way that you find yourself calling the same method with the same parameters every time. That method is still a generic method. There's a reason for it to exist, but you call it with the same parameters, go through the same work, get the same conclusion from that, and plug and play that into a grander argument. So we can refactor code to reduce code duplication, a very important thing for us to do. But algorithmically, the equivalent of that is recognizing when we are asking the same question over and over and over again and going through the calculation to get the answer. So when you find yourself copying and pasting code, there's always a better decomposed solution. Call the code that you just wrote, or wrap it in a method and then call that method whenever you would be copying and pasting that code. We can do exactly the same thing with parameters and methods. If we are going to call the same method with the same parameters and go through the work to get the same return value, then we should have cached that value. We should have stored it in some structure where, instead of going through the logic of recalculating something that we already should have the answer to from prior work, it becomes a lookup and a table rather than a recalculation. So I'll motivate this in 10 minutes by looking at the Fibonacci sequence. Shows up all the time in computer science, but the way we calculate Fibonacci from top down and bottom up is a little bit different. What do I mean by top down and bottom up? Let's find that out. I asked you, what is the 8th Fibonacci number? How do we calculate it? How would you go through the process of calculating the 8th Fibonacci number without access to a calculator or the internet or anything else? All you have is you and paper, and I ask you for the 8th Fibonacci number. How do we do it? Yes.
Go about the process.
Yeah, so the 0th Fibonacci number is 0. The first one is 1. Then we just add 2 together. That's our 2nd Fibonacci number. Add the last 2. That's our 3rd Fibonacci number. Add the last 2. That's our 4th Fibonacci number. Add the last 2. That's our 5th Fibonacci number. Add the last 2. That's our 6th. Add the last 2. That's our 7th. Add the last 2. That's our 8th. That's not a terrible process, right? That didn't take too long to answer. That is a bottom-up solve of Fibonacci. You're taking you're starting at the base case, and you're going through a loop, basically, that is calculating the next number based on the information that we have. Nowhere in there did we need to look things up. But imagine that instead of implementing this iteratively, we were implementing this recursively. What would need to change in order to implement this recursively? Thinking now top down in terms of, if we're solving Fibonacci of 8, we need solutions for Fibonacci of 7 and Fibonacci of 6 to be able to calculate Fibonacci of 8. So I'm going to redraw this in terms of a tree. I'm just going to create a number that is the solution to Fibonacci of 8. Recursively, this would break down into Fibonacci of 7 and Fibonacci of 6. 7 would break down into Fibonacci of 6 and Fibonacci of 5. 6 would break down into Fibonacci of 5 and Fibonacci of 4. 6 would break into Fibonacci of 5 and Fibonacci of 4. 5 into 4 and 3. 5 into 4 and 3. 4 into 3 and 2. And you start to see that we're repeating some work. If every single one of these broke all the way down to something that we know, if we could say that the base cases of this recurrence are t of 0 and t of 1, the Fibonacci numbers that we know as an immediate lookup without needing any further calculation, how many times are we doing something like calculating Fibonacci of 4? And each one of those involves a further breakdown of work that we, by the time we do this the first time, have already done, and we should be able to look it up. There is no reason that this process should actually be any less efficient than this process, just because of how we've done it. But if we don't store the subproblems as we calculate them, then it ends up being significantly more work. Asymptotically, how much work was this iteratively? If n is the nth Fibonacci number, how many calculations did we have to do in order to calculate the 8th Fibonacci number? Approximately, asymptotically. It's n. It's an order based on n. There is a constant ahead of that, and that if we're keeping track of different variables, like what is first and second, calculating next by moving these over, it's a constant times n, something like 3 or 4n. But it's linear. If we're not trying to reuse subproblem solutions as we calculate this in a tree, what is the total number of subproblems that we are solving here? What order is this in? Someone on Zoom correctly guesses that it's exponential.
Yeah.
How many copies of 8 are there? There's 1. How many copies of 7 are there?
1,
1. How many copies of 6 are there?
2,
How many copies of 5 are there?
3.
Oh my God, it follows the Fibonacci sequence.
Yeah, it does.
The number of subproblems for the Fibonacci sequence break down into the Fibonacci sequence. That's a fun discovery. If we drew this out, we would see that to continue to be the case. And the Fibonacci sequence is growing exponentially. Interesting to see. But imagine if, when we calculated Fibonacci of 6, we just kind of put this on hold. If we do this as a depth first search, we go from 8 to 7 to 6 to 5 to 4 to 3 to 2 to 1 and have a lookup at that point. If we store Fibonacci of 1 and use that as we calculate Fibonacci of 2, and we store that and use that to calculate Fibonacci of 3, and store that and use that to calculate Fibonacci of 4, we've basically done this work and can fill out when we reach the top level. We don't need to go through any of this work. We just go back up the recursive chain, solving every Fibonacci that we get, and 8 is 7 plus 6, and 6 is a lookup there. So we carved off that entire part of the tree. And what we've done is we've changed this from an exponential complexity into a linear complexity problem that much closer mirrors this process than the process that we were going to go do. So the purpose of dynamic programming is to take something where the repeated subproblems from this add a significant complexity to the problem and break it down to where if we store that information, how frequently can we look it up instead of have to recalculate it? And we find very frequently that this leads to a drastic reduction in overall complexity for the implementation. I guess before I erase things, questions on that?
Yeah, that's one. I'll say right there.
Yeah, it does. It looks very much like a binary search tree. And when you see that that structure is mirrored, like this subtree is that subtree, then you can see how when a binary search tree requires, we can fit an exponential number of nodes into a depth of size n. There become an exponential number of nodes based on a depth of size n when you're solving this tree. And it's not about that, we're not asking questions on the depth of this tree. We're actually going through and requiring solutions for every node in this tree. There are going to be an exponential number of nodes of the tree based on the depth, which is the n. Now, n is the depth. How much calculation do we need based on n? It grows and is exponential. The rest of the slide will just go through and say what I have already said. But it's worth going through just to say it. How do we calculate it? Usually we take a bottom-up procedure when we recognize that's really easy. So we use the bottom-up approach very early, but we'll use the known values, those base cases of the recursion, Fibonacci of 0 and 1. From there, we calculate Fibonacci of 2 and go through an iterative process. So we solved it top-down. We looked at the subproblems of Fibonacci of 8 and what subproblems make up those subproblems all the way down the tree. Found that there was repetition inherent in the structure of the problem. So rather than trying to solve the problem brute force, if you recognize the structure of the subproblems, we can look at what are the subproblems, solve the subproblems, store the answers to those subproblems so that they become a lookup rather than a recalculation when we see them again. Because we, the programmer, knew there was going to be some repetition in this substructure. So we should store it because we're likely to be asking the same question again in a bit. So the options to store this were just always solve the problem bottom up or solve it top down and recursively store the answers to subproblems rather than trying to look them up. Once we have the answer to a subproblem, add the solution to some data structure that we're using to store that, then we can look it up directly. Whenever we see a problem, we will first look, have we already calculated its solution? If so, there's the answer. If not, then go through the work to calculate the solution. But once we've done the work once, we store it in the table so that in the future, it's a lookup. Questions on that? On that idea? This idea shows up everywhere in complex algorithmic design. So whenever we're doing some kind of optimization problem, dynamic programming seems to show up very frequently. Typically, thinking about a problem and asking, does dynamic programming apply here? You can take 4 steps to answer that question. The first would be, what is the structure of an optimal solution? This allows us to break down the problem into its associated subproblems. What is the structure of a solution? For each problem of a particular size, how many subproblems do we have? What is the complexity of those subproblems? So then we recursively define the value of an optimal solution. So the solution to it's very much like recursive thinking. The solution to the optimal solution to this problem is recursively defined in terms of optimal solutions to subproblems. Then we say, how can we compute the optimal solution? And again, usually this is going to be in some kind of bottom-up solution. Or if we have to break it from top down, like we did here in this tree, we'll look for those repeated subproblems. And then again, constructing the solution from the computed information that we have. So this looks just like the steps of recursion. The reason we study recursion and recurrence relations right before something like dynamic programming is the inherent structure of dynamic programming relies on your ability to break down problems recursively. Even if you're going to solve it iteratively, an iterative solution is really just a bottom-up solution to a recursive problem that if you solved it recursively would be some kind of top-down process. So solve it iteratively, that's bottom up. Solve it recursively, that's top down. If you are going to solve it recursively, then you can map it onto that same type of procedure that works well bottom up by recognizing those repeated subproblems. So we will come back to this. I'll let you sleep on that for a weekend, and we will come back to coming up with some examples of this. The main example that I'm going to show you involves an algorithm out of bioinformatics, which is DNA sequence alignment. You can determine how related two organisms are to each other by looking at the similarities in their DNA sequences.
Hey, I actually have a quick question about the homework we've been looking through.
Yeah.
So for the book problem, I don't entirely remember hearing this again, and I apologize for asking again. If you did mention it, but were you expecting us to submit like a document talking all the book problems questions or?
Yeah, that'll be an additional piece of that. It could be in your zip.
Yeah, I thought earlier, I was thinking the same thing anyway, so. Just gonna probably just be something that is, the name, regarding the naming, I guess, for that.
We just put it all in comments in our code.
Could do that too. That would be fun to make the graders find.
Actually.